Good morning, everybody. Salamat pagi, salamat siang, salamat sore, salamat malam. Good morning, good afternoon, good evening, and wherever you're watching from. My name is Gabriel Chukwemeka Victor, and I'm the presenter of this presentation. This is slide through inverse of a matrix. Inverse of a matrix. Now, in this lesson, we're going to be looking at introduction to inverse of a matrix, methods to find inverse of a matrix, applications of matrix inverses, excuse me, and challenges and advanced topics. So, first of all, we look at introduction to inverse of a matrix. A square matrix. The definition of matrix inverse initially. The property of matrix inverse. A square matrix A has an inverse if there exists another matrix B such that AB is equals to BA, that it's just a transpose of AB equals to I, where I is the identity matrix. The inverse of A, of matrix A, if it exists, is usually denoted by A raised to power minus 1, that is inverse sign. Then the conditions: only non-singular matrices has an inverse, meaning the determinant of the matrix is non-zero. That is, only singular matrices has an inverse. That is, if the condition whereby you can have a matrix that can have an inverse is if the determinant is not equals to zero. If the determinant is equal to zero, it doesn't have an inverse, meaning that it is a singular matrix. Concept of multiplicative identity. Identity matrix, excuse me, identity matrix. The identity matrix I of size n times n, that is an illustration now, is a square matrix with all diagonal elements as 1 and all other elements as 0. It acts as the 1 in matrix multiplication such that A times I is equals to A. Role in inversion. For a matrix A to have an inverse, multiplying A by A raised to power minus 1 must yield the identity matrix I, highlighting its central role in inversibility. That is the concept of multiplicative identity. Now, conditions for matrix to be invertible. First, square matrix, in the sense that only a matrix that has equal number of rows and columns can be inverted, has an inverse. If the matrix doesn't have equal number, if it's not a square matrix that have an equal number of rows and columns, it doesn't have an inverse, because it's only for square matrices that the dimension after multiplication will be preserved. If you multiply it, the dimension will still be preserved. The square dimension will still be preserved. If it is not a square matrix, the dimension will be different, it will change. 2. Non-zero determinant. A matrix A is invertible if and only if the determinant is not equal to 0. If the determinant of a matrix is equal to 0, it cannot be inverted. It can't be inverted if the determinant, if the determinant equals 0, meaning that it is a singular matrix. Singular matrices cannot be inverted. They are non-invertible. Then next, linear independence. The rows or columns of A must be linearly independent, ensuring that A spans the entire vector space, a requirement for invertibility. That is the requirement for invertibility. Excuse me. Then unit 2, methods to find the inverse of a matrix. The first method is what we call the Gauss-Jordan method. The Gauss-Jordan method is a method whereby the rows are reduced and then the rows are like they are reduced rows and then you switch the rows. Row reduction is the first step in this Gauss-Jordan method. Use elementary row operations, that's ERO, that's a method to transform the matrix into its identity form while simultaneously performing corresponding operations on an augmented identity matrix. Second step is systematic approach. The process involves pivotal steps including swapping rows, multiplying a row by a scalar, and adding slash subtracting scaled rows to achieve row echelon form. That is systematic approach. Then practical challenges. The Gauss-Jordan method can be computationally intensive for larger matrices, but is effective for smaller, well-behaved systems. That is the practical test. The Gaussian method can be computationally intensive for larger matrices, but is effective for smaller and well-behaved matrices. That's matrices that are just in normal form, that are not too big, too large, too complex. That's what we call well-behaved systems. Determinant and adjoint method. This is another method for finding a inverse of a matrix. This method, let me just explain it in a sense I understand. This method is when you you find, first of all, you find the determinant of the square matrix, that is the matrix that is given, the given matrix. You find the determinant. Then after you find the determinant, you when you find the determinant, you find the determinant is not equals to 0. Then you start looking for, when you find the determinant, then you use the adjoint, that is the transpose. In other words, when you transpose the matrix, that is when you find determinant and determinant is not equal to 0, meaning that it has an inverse. Then the next step is for you to transpose it and add the necessary signs. Where minus signs will be put minus sign, it has rules though. It has the rules. So we put minus sign where some minus sign will be, and put plus sign where plus sign is supposed to be. That is this determinant and adjoint method. But it's usually more complicated in a 3 by 3 matrix when it's much bigger, because you find the smaller cells. After you find the determinant of a 3 by 3 matrix, you find the smaller cells of it. Then with those smaller cells, with the smaller cells, then after you find smaller cells, then the matrix will now be more bigger. Then you multiply it by the determinant. Then later you find the transpose, that is the adjoint of it. That is when it comes to 3 by 3 or more complex matrices than that, 4 by 4, 5 by 5, and so on. Then this is now method 3, applications of matrix inverses. Let's go. First of all, solving system of linear equation. Effective solution. Excuse me. Matrix inverses enable direct computation of solutions for linear equations in the form Ax equals to b, avoiding iterative methods. That is the effective solution. The simplification using the inverse x can be expressed as A inverse b, A is 1 minus 1 b, simplifying the process by large scale system with consistent coefficients. That is simplification. Then verification. Matrix inversion offers a way to validate solutions by remultiplying Ax and ensuring it equals b. When you multiply Ax, that's not verified whether you verify it. The matrix, you have to multiply Ax and ensure that it is equal to the the counterpart B. Then now, computer graphics and transformations. Graphics and transformations. Image manipulation. This slide shows how matrix inverses are essential in a computer graphics. In image manipulation, we use matrices to transform images like scaling or rotating, and the inverse and the inverse lets us undo those changes accurately. Sorry, excuse me. In coordinating remapping, inverse matrices allow us to move between different coordinate systems while keeping positions consistent. And in on distortion, they they help. That is not distortion. That is the third one. They help correct images distortion, such as those caused by camera lenses. So the key idea is transformations change change the images, and inverse matrices bring it back to correct it, ensuring accuracy in graphics. Now, engineering and optimization problems is another thing that matrix inverses can actually fix. This is how matrix inverses are applied in engineering and optimization. In control systems, inverse matrices help analyze system stability and design feedback mechanisms. In data fitting, that's this one, in data fitting, especially methods like least squares, they are used to minimize error and improve the accuracy of models. And in resource allocation, matrix inverses support solving optimization problems, helping us use limited resources efficiently. So overall, inverse matrices are key tools for making systems stable, mo- models are accurate, and decisions optimal. 4. Challenges and that is unit 4. Challenges and advanced topics. Non-invertible matrices, that is in other words singular matrices, that is the ones that has the determinant of zero. Determinant criteria. A matrix determinant of zero is singular and lacks an inverse, reflecting linear dependency among its rows and columns. That's in other words, a matrix with that has a determinant of zero is not it lacks an inverse, doesn't have an inverse, as I said earlier on in the video. It is thereby reflecting linear dependency amongst its rows and its columns. Real world real world implications. Singular matrices arise in scenarios with overfitting or redundant data, complicating computations in systems like linear equations. 3. Alternative approaches. Non-invertible matrices often require approximation methods or adjustments such as regularization to address their limitations. That is the alternative approaches. Now, computational complexity. Large matrix challenges. Inverting large matrices depends considerably on the computation resources with complexity scaling cubically. I don't know this one. I don't understand. Thank you very much for listening. Thank you all for being here for listening, and God bless you all.